Good morning. My name is Meg Deloff, and I work for USGS PNAMP. Thanks for joining us for the April 2023 meeting of the PNAMP Fish Monitoring Work Group. A couple of housekeeping tips before we get started. Please mute yourself by clicking the microphone icon on your Teams platform. If you're on your phone, you can use *6. Also, please turn off your camera when you're not speaking. It kind of helps people stay focused. If you don't see the toolbar, try moving your mouse and it should pop up. You should see a bar that looks similar to the one that's on my screen, depending on whether you're using the browser or the desktop version of Teams. If you have any questions or feedback, please use the chat function or raise your hand and unmute yourself. Just a note, we can mute you, but we cannot unmute you. We'll be recording the meeting and it'll be available on our YouTube channel in the next few days. If you're having trouble with the chat function, here's a couple of troubleshooting tips. Try leaving and joining again. Using a different browser, Edge typically works better than Chrome. Try using the desktop version instead of your browser or vice versa. If you don't have access to the chat, always feel free to unmute yourself and comment or ask questions. A quick reminder that in an effort to keep this an open and welcome environment, please remain respectful. Now, if the Fish Monitoring Work Group core team will turn their cameras on and introduce themselves, that would be spectacular.
This is Russell Grande without a camera. I'm sorry.
Hey, Russ.
I guess I can go. I'm Marika Dobos with Idaho Fish and Game.
Awesome. Thanks.
Hi, I'm Jen Bayer with USGS and PNAMP.
Okay. You can't see my participant list. Casey Bleesner with ODF&W and Nancy Leonard with PSMFC are unable to join us today, so they're also part of our core team. And Lara Erickson with PSMFC if she's out there. All right. Thanks, everybody. Now it's your turn. Don't worry about turning on your camera or your microphone. Simply open up the chat and introduce yourself with name and organization. This will acquaint you with the chat function and also helps us keep track of participation. And then while you guys are doing that, I'll just quickly cover today's agenda. So first we'll cover task updates. And next, Ben Staton will present on integrated population modeling of Grande, Ronde, spring Chinook salmon. And then we'll wrap up with next steps. And with that, here we go. Leads for each current task will give an update on progress, like I said. And then I will pause briefly after each update for questions or comments. If you have a question after we move past a task, feel free to type it in the chat and I will circle back after all the updates are complete. And obviously, if you don't have access to chat, you can also unmute at the end of the task updates and ask your questions or comment. And with that, I will hand this over to Morgan Bond with NOAA for the carrying capacity standards update.
Yeah, thanks, Meg. So just a quick reminder for folks what the carrying capacity team is all about. So carrying capacity is really something that is being estimated in lots of places and using lots of different methods. And so this team is really trying to come up with some documentation to really help people sort of navigate the variety of quantitative methods that are being used to estimate capacity, different data sets that are going into those, and then the different types of outputs that we get from those different methods, and really, you know, what's useful and what's comparable under different circumstances. Because these methods are so varied, that we have tried to put together a sort of a broader group to help write a document that we're sort of calling, for lack of a better term right now, our best practices document. So this is really a document to try to make something of all these different methods kind of in a single place that people can refer to really get a handle on either when they read something, you know, what to make of that, or if they're trying to develop some capacity estimates for their own work, maybe based on the data that they have in hand, what approaches to use. And so to date, we have put together sort of these outlines for the best practices document. And then we've now approached all of the authors for those individual quantitative methods that are outside of our group to ask if they would write a section sort of detailing their method and this sort of individual section outline for those. We have authors for all of those sections now. There's about 5 different methods that we're including in this. And so those sections should be done by May. And then hopefully end of June or so, we hope to have a draft put together for that best practices document. So that's where the carrying capacity standard team stands today. Thanks.
Awesome. Thanks, Morgan. Next up, we have juvenile density, snorkel, and electrofishing, and Russ will handle this one.
Yeah, this is pardon me. This is Russell Scranton with BPA. The update that we have is that we completed a draft data exchange standard and made a request with the data exchange standard or an exchange that would look at controlled vocabulary to acquire juvenile distribution and density data. We had a general data call to have people supply their data sets across the Northwest for Chinook and Steelhead. We had 10 organizations, IDF&G, CritFic, Oregon State University, King County, Bioanalysts, Confederated Tribes of the Warm Springs, WFW, another data set from ODF&W and U.S. Forest Service have all provided data in that standard. And that's been provided to Dan Isaac and his team to update a potential fish density distribution analysis tool. And the other component of it is with that data standard, we provided some information and coordinated with StreamNet. And one next step will be to potentially further discuss with the XCOM and steering committee what it will take to incorporate that data structure into StreamNet. There are things that we uncovered in discussion with StreamNet specifically related to the stream networks that are used and how people identify sites, whether it's river kilometers or latitudes and longitudes, but there's big differences between how StreamNet's data exchange standard and some site-specific standards are documented. So that will be a next step, is to continue to meet with StreamNet steering committee and potentially XCOM to discuss the future potential incorporation of updates to a data exchange standard for juvenile density and distribution. And there will be, we're working on figuring out a fall timing for a potential follow-up and meeting, and also distribution and sharing updated results from the analysis that Dan Isaac's team is producing. That's it for the fish density exchange task.
All right, awesome. Thanks, Russ. And I forgot to do this after Morgan's, but if you guys have questions or comments for the carrying capacity or the juvenile density, I'll just pause real briefly. And Amy, if you see any come up in the chat, I can't see it right now. So if you would just read those, that would be spectacular. Or if you want to raise your hand and feel free and unmute and ask a question if you don't want to type.
Yeah, I'm not seeing anything in the chat, and there are no hands raised.
Okay, groovy. Carrying on. Next up, we have Evan Brown with IDF&G.
Morning, folks. If you notice, we have changed the name of this task just a little bit in order to avoid a little bit of consternation, which we've had regarding the term populations. So it is now just a more generic term, fish management unit, boundaries and attributes, with the idea being that it will include both populations, local populations, core areas, migratory corridors, all of these different polygons representing fish management units and analysis units in general. The reason being is there's a lot of similar terms from taxon to taxon, and so we just wanted to be a little more general and clear, and not worry folks that we were going in trying to redefine, reshape their populations. So we have a proof of concept done. We have presentation that we are going to send around to this specific work group, and then we will bring it back to the whole group after we get their feedback. That's what's up next. If anybody has any questions, feel free to contact myself or Van Hare. With that said, I'll take any more questions. Otherwise, we'll just move on.
All right. No, thanks, Evan. I'll pause for a minute and see. And Amy, again, just let me know. You guys got to be fast if you want to comment.
Yeah, you can take your time and think about it if you want. If you'd rather just wait for the email with the proof of concept and the presentation, that's fine too.
All right, I'm not seeing any hands or comments in the chat.
Thank
All
you.
right, cool. Thanks, Evan. All right, I'm just going to cover rotary screw trap operation real quick. We had 2 meetings in early 2022, but we're on hiatus for a bit due to staffing. Some of our task leads had some folks retire in their agency and needed to take on additional work. So we took a bit of a break, but we're on track to reinitiate the tasks soon, likely probably the end of May, with plans to meet with PSMFC to discuss StreamNet's dashboard for screw traps and whether or not there's potential for collaboration. We will, oops, sorry about that, guys. We will continue to work on recommendations for data exchange in regards to site summary data. And that's kind of the brief update on that one. Russ or Marika, did you have anything you wanted to add to RST?
Nope.
This is Russ. I'll say one quick piece, which is just one of the findings that we did have, and it was a question before about uses and applications. Right now, there is the coordinated assessments exchange for out-migrant summary information. The question came up through the Columbia Basin Tributary Habitat Strategy that screw trap data, timing, condition are data sets of interest for exchange and sharing. So that's what the group will be continuing to look at, is how do we refine and summarize some of those other data sets besides some of the other related data from screw traps besides the high-level indicator. Thanks.
Awesome, thanks, Russell. And then I'll pause briefly for questions or comments. Alrighty. Next, Marika will talk about the pit array and related pit tag analysis task.
All right, so this is our newest test that we just started. So I'm actually still looking for participants. We have some participants from an old survey list, so I'm looking for people who are willing to actually actively participate in this. So this is going to be kind of a multi-stage task. There's many parts and pieces to it. Essentially, pit tags are a fairly new bit of technology that continues to progress, and many people are using it for evaluating habitat, estimating abundances into tributary systems, at hatchery racks and whatnot. So there are still tools that I think can be useful. So the first part that we're trying to tackle is actually working, first of all, on the data management side, working with Nicole Tancredo and John Tenney. They've actually put some new tools in Pitagis that allows some of the metadata that are collected at pit tag arrays to be looked at and analyzed through Pitagis, which is looking to be some pretty cool tools. There are still other ancillary data like environmental data that we have yet to try and figure out where the best way to store those data and how to summarize those data and tie that into the pit tag detections. So that's going to be something we're going to look into. And then the other part is working with the in-stream pit tag detection steering committee. They're kind of working on the nuts and bolts of pit tag arrays, of looking at standardized approaches and ways to store information on the equipment that are being used at specific sites, the type of data storage, whether it's MUX or master controller systems or cheese blocks or whatnot. There's a lot of variation in the equipment that are in the ground across the landscape in the Columbia Basin. So they're working to try to build some standardization on how sites are entered in Pitagus, to look up records and some way of storing some of those kind of nuts and bolts information, and how some of those parts are in use. So we're trying to work with that subcommittee to make sure that we're not doubling up on effort, that those folks are the pit tag experts. They're the biologists that are deeply involved with the use of pit tag arrays. And so they're going to be important folks to pull in and work with to try and accomplish our tasks. And then the other part that we're going to try to tackle up front is data management tools outside of Pitagus. So if you've ever worked with pit tag interrogation data, it's really messy. For example, if you're trying to pull in abundance estimates, variables that determine adults or juveniles can be highly variable across your systems. It can be very time consuming to try and clean the data that you need for your analysis. Some folks have built tools that are specific to certain systems, like the Snake Basin. So we want to work with the people that have already built those tools and glean that information to try and either modify those tools to make it more flexible for other systems, or build tools for other systems, and also just kind of have a housing place to store where these tools can be accessed by biologists. And whether that is going to go through Columbia Basin research or GitHub, if it's R-coded or what, those are kind of the things that we want to try and figure out so that we can get tools available to biologists. Try to make modifications for folks where we can to improve those tools for use. And then down the road, kind of the next step would be to tackle some analytical questions we have with pit tag arrays. There's a variety of methods out there to determine site efficiencies, whether they're used for survival estimates or abundance estimates for adults or juveniles or whatnot. They're a tool that can be used for a lot of different questions, but there's not a lot of standardizations, and some of these analytics haven't been quite figured out yet too. So that's kind of the next step once we tackle the data management aspect of it, and again, tying into the pit tag steering committee on some of the nuts and bolts of if new sites are created, what kind of equipment are they using, standardizing how they are entered into Pitagus as an interrogation site so that we can use that information for more landscape-wise analysis that can be comparable from system to system. And Russell, if you have anything to add to that, it's a lot. It's a big task. That's why I'd like to chunk it up a little bit and try to take care of the low-hanging fruit that we know we can handle in a short amount of time.
Yeah. Thanks, Marika. There's only one other concept or a piece that this group could take on, which is just looking at with PNAMP and PTAGA steering committee and others, improved ways to look at documenting tagging designs. How do we coordinate better, just understand the total sample sizes of fish that are being tagged. So that's one other small topic that would be managed with all the other ones. So it's as Marika said, there's quite a bit. We're trying to make it manageable and discuss priorities with people who are interested. So thanks, Marika.
Yep. And then I guess the one update is that the in-stream pit tag steering committee is going to be having a meeting next month on the 25th. So we're going to be working pretty hand in hand with that committee. So I'm going to be actively participating in those monthly meetings to work with that group to make sure that we can kind of outline tasks and have a better idea of the things that we need to tackle and try to come up with a group of participants so that we can start working on these products.
Marika,
Mm-hmm.
did you want to mention AFS?
Oh yeah, thank you for reminding me. So there, we don't have a symposium, but there are a handful of folks, Rebecca Buchanan, Brian Mashoff, and Jennifer Goslin, I believe, that will be presenting on some tools that, well, Jennifer and Rebecca work for the Columbia Basin Research. I saw Jennifer's on the list and she's on the call today. So they are presenting on some tools such as that are provided to folks through Columbia Basin Research or other avenues that folks can use that mainly revolve around pit tag data and how to manage that and how to like use these tools to easily pull out pit tag information for data analysis. And I don't know if I want to go into any more depth on that, but they will be presenting as a group in one of the contributed sessions at AFS. So if you're gonna be there at Western Division, there'll be those talks. And I'm also co-chair of the Anatomist Committee, so I'm planning to have an invite to folks to participate at the Anatomist meeting. And if they want to further talk, we can have kind of an open discussion on tools and what are useful for folks, what aren't useful, what can be changed to make it more useful, and try to answer some of those questions.
Awesome. Thanks both Russ and Marika. That was a great update. And we will pause one last time briefly for questions or comments. Feel free if you guys have thought of any questions for any of the earlier tasks, type those in the chat or raise your hand and unmute, or you can just unmute. And I'll just give this like a little bit. And Amy, again, let me know.
Yeah. So
Hey, Meg, and oh, go ahead, Amy. Sorry.
Okay.
Casey, I saw your comment, Casey. So I haven't reached out to Fred. I've been working with Derek Faber is now one of the leads for the in-stream pit tag steering committee. So I will reach out to Fred and see if he's willing to help out where he can. Thank you.
No problem. Thanks.
All right, Jen and Amy, did you guys have anything, or was that?
That was it. I was just going to read Casey's comment, but Marika's on it. Don't see anything else.
All right, awesome. All right, next up is our tech talk. I am honored to introduce Ben Staton. He's a quantitative fisheries scientist with the Columbia River Intertribal Fish Commission. He's going to talk about integrated population modeling of Grande spring Chinook salmon, linking dynamics and habitat to monitoring data via SSMs. And with that, I will relinquish control. And Ben, the virtual world is yours.
Okay.
Appreciate that, Megan. Here, I'll get my screen share all set up.
All right, looking good.
Okay, I was just about to ask. All right, so really appreciate that introduction, Megan, and for the invite to give this presentation here today. I'm really excited to be here and talk about this modeling project that I've been working on with our team of collaborators. So I think without any further ado, we'll just jump in and
Oh, Ben, you got muted.
okay. Little pro
There you
tip
go.
for those of you who are used to using the space bar to advance your slides. It turns out in Teams that will mute you, so maybe don't do that. Okay,
Awesome.
so just to give a kind of overview of the project as a whole, we're kind of trying to answer this really kind of large research question, which is having to do with how likely different management actions that we might be able to take today or over the next decade or so, how likely might those be to result in population recovery of some of these Grand Ronde populations in the face of the current challenges that they're facing and the future challenges that they will be facing. So, of course, really big question. I kind of think about the project as having three parts, and we're really only going to get a chance to dive into one of them today. So the first step really is to quantify these, what we might call life cycle parameters and population dynamics based on the historical data sets. So grounded in empirical truth, sort of best available knowledge is the data sets that we have. And so we're going to combine those, try to estimate relationships between how one life stage might affect another life stage, and how these things vary interannually. That's kind of step one. And that's the model that we'll be talking about today. And then once we have output from that first model, then we can kind of sit down and say, well, this is how we think the future might change. Well, there's going to be a lot of habitat restoration going in, but there's also going to be some climate change happening. How are those things going to interact with each other? So that's kind of step two, is to talk about different scenarios for how the future might look. And then the third step is to combine steps 1 and 2, take the output from the past, take our scenarios for what we think the future might look like, and try to simulate the population dynamics forward, and then characterize performance metrics of that might reflect how likely population recovery is to be. So that's kind of the overall project. The three parts, we've got the statistical life cycle model as step 1. Step 2, you might call those like hypothesized or hypothetical states of nature for the future. And then step 3 would be the simulation life cycle model. So project is bookended by two life cycle models. One is all about estimation, another is about simulation. So that's kind of the project as a whole. And this is the part that we'll be talking about today. So to talk more about the model itself, some about the scope that it's covering, talking only spring Chinook salmon in the Grand Ronde Basin. We're up here in northeastern Oregon. This is a tributary of the Snake River for those that are not familiar. There's 4 populations within this basin that we're sort of modeling as distinct spawning groups. Upper Grand Ronde, Catherine Creek, the Lostine River, and the Minam River. And this map here shows where they're located. And then, of course, there's, it's not just that there's populations, there's structure within populations too. So, we talked about the data that we have being expressed in terms of time series. So we've got, we want to be modeling different years separately from other years. And then we've got data on different migratory strategies that juveniles can take. They're monitored sort of at separate times, and so it makes sense to model them a bit differently. Of course, the rearing type, the origin, if it's a natural spawn fish versus a hatchery spawn fish, we'll track those separately, as well as the age that these fish return at to spawn. So that's kind of some structure that will each level of that structure we're going to try to treat a little bit differently from the other levels within that structure in the model to try to characterize as much heterogeneity as possible in these things, because it could end up being important. Of course, to estimate all of that complexity, you need a lot of data. And luckily for us, of course, a lot of data do exist. And got to give my hats off to Polly Gibson with ODFW. She's kind of led our, as a member of our team, she's sort of been the data person that compiles all the data and gets it all nice and cleaned and tidied up for me to pass into the modeling. So I wouldn't really know where the first step is to start with that process. So really helpful there. So I mentioned we've got 4 populations, but the nice part about it is that all 4 of the populations have really, really similar monitoring programs. And so the model can be really pretty much almost, at least in the treatment of the data, can be very, very similar among the 4 populations. The one exception there is the Minam. That's in a wilderness area, and there's no hatchery or a weir system on that basin. So a little bit differently there, but that's really the only main difference. And so I think about the data sources that feed into this model as being sort of 3 main categories types. We've got sort of abundance, then we've got survival, and then we've got composition. And length got added in kind of as a last, more of a recent thing. And so I've kind of clumped that in with abundance. But so, if we're talking numbers of fish, how well they transition into the next stage, given that they survive to one stage, how likely are they to make it to the next stage? And then the composition, mostly speaking in terms of upon return as adults, we need to know what fraction of them are of each age and what fraction of them are of each origin. Those are the main data sources that are feeding into this model. And then the other thing I'll just mention quickly is that we're talking about survival. Of course, raw data for survival a lot of times comes in the form of like pit tag detections. Those data have already been analyzed independently of our model. We're taking the pre-compiled survival estimates along with their estimates of standard errors and uncertainty, passing them to our model as kind of data after they've been externally estimated already. So just to kind of give you a notion that a lot of the data that we're talking about are actually estimates that have been passed through another model at an earlier stage, but they're still in a pretty raw format. Okay, so moving on away from the data, talk a little bit more about the modeling framework. So I think of this model as being kind of an integrated model in that it fits to a lot of different data sources all together, and it's got one big joint likelihood function that explains all of it. And it's not just integrated from the whole life cycle all in one model. It's also integrated in terms of there's 4 populations being fitted at once. These 2 origin types are fitted at once, and these about 30 years of monitoring it's all being fitted in the same model. So that's kind of what I mean by it being an integrated model. The next thing that you could use to describe this model is we're fitting it using the Bayesian mode of inference. Basically, what that means is that we're really, when we're looking at the output from this model, we don't really care a whole lot about an exact point estimate for a parameter so much as we do about the relative support of different parameter estimates. So that's kind of one way of talking about Bayesian. The other big thing about using a Bayesian approach is that we can incorporate any kind of prior information. Like if some of our parameters are very difficult to estimate because there's not a lot of data or information in the data for it, it's possible that another study might have good information on that parameter, and we can the Bayesian approach allows us a rigorous method of sort of borrowing that information. Then the last kind of way that you could categorize this model would be to call it a state space model. And that kind of just means that the model is separating out the creation of a data set into 2 processes. Both of them have got randomness in them. One is due to the part that we really care about quantifying, and that's the biology, what we call the process submodel. That talks about your expected population dynamics and how much variability in the data is due to background environmental variability. And then there's the parallel process that's going on in the model that talks about how we monitor that system. How do we make observations off of the fish and the survival terms? So, and there it's also accounting for variability just due to sampling. So we've got process variability, sampling variability. The state space model allows you to separate those two things out. And so that becomes kind of nice because we don't really, from a simulation perspective, we don't really care about simulating variability due to observations. We just care about simulating variability due to underlying population dynamics. So a lot of details there. Really, the main take-home message here is that the model really just tries to estimate the value of unknown quantities, as an example, like a par capacity term, based on these data time series, and it tries to do that in a statistically rigorous way. And so what do I mean by statistically rigorous? Well, the kind of four main things that I'm talking about here. One is that there's variability in the data beyond the biology, and that's kind of what I just talked about. And by accounting for that extra variability, the idea is to try to help guard against what we call observation error bias. And that has the tendency to prevent us from characterizing relationships that are actually there just because there's a bunch of noise in the data that we wouldn't otherwise be accounting for. So that's one thing that's nice about this approach. Another nice thing is that it acknowledges that the state variables are linked in time. So for example, par that recruit in a given year are produced by spawners that return the previous year, but those par will become spawners in the future and become the next. If you envision like a spawner recruit relationship, the par will become spawners in the future, and so they're not independent, they're linked. And if you ignore that, you can get into some nasty problems that we call kind of as a whole this time series bias problem. And by using this sort of state space modeling framework, it allows us to at least worry about that quite a bit less. The other thing is that it does allow us to capture linkages among life stages and capture things that we might consider to be delayed effects. That if you were to analyze the data sets as in terms of just one life stage moving to the next life stage, you might miss some of these linkages and delayed effects that you can capture by modeling it all in one life cycle model. Other advantage of doing it all under the hood of one model, it forces the model to be consistent with all of the data sets that are available. And so if you think about the model as being an expression of a hypothesis or an expression of our best available knowledge, if the model doesn't fit the data very well, then that kind of tells you that you've got a poor hypothesis or that you need to rework your thinking behind the system a little bit. And then one other thing, we won't really get to talk about this a whole lot, but by modeling the four populations into one model, we can capture any correlations between them. So, you know, if you might think that if survival is better than average for one population in a given year, there might also be reason to think that it's better than average for another population in that same year, and likewise for worse than average years. And it turns out there's quite a bit of evidence for that in these populations that discovered that early on. And so that was a feature that we wanted to build into these models. And one thing that can really help with is if there's portions of the time series that have got data for all the populations, but then there's another portion of the time series that has data for most of the populations, but not for one of the populations, you can use the correlations that you've estimated in the time periods where they share data to help inform the time periods where they don't share data. So that's another really nice feature of modeling these dynamics as being correlated in time. Okay, so moving on to another kind of important thing that the model has to do is tease out density-dependent dynamics. So this is something that is really important with modeling salmon population dynamics, and it's really widely observed that the salmon populations have this feature where demographic rates tend to decline with increasing density. So a demographic rate might be growth rates or survival rates, those kinds of things. And the idea is that if there's more fish, there are fewer resources per fish, and so fitness declines on average. The average fish is just more fit at low population densities than at high population densities. And a feature of that is that it does help guard against extinction. If you only have 2 fish left and they would do better than they would do otherwise, it can help guard against extinction. But yeah, it is really important to account for in population modeling, because it does help ground us. We can't just have ever increasing population density and expect that the survival will go unchanged forever. And so, the things that we're hoping the model can help inform us about is the strength of this density dependent effect, the timing of it, at what point in freshwater does it occur, and what are some plausible mechanisms behind it. So, and I did mention that this model has big ties to habitat. That's a big aspect of what we're trying to do. So it's important to think about density dependence as being kind of mediated by habitat availability. And so one way to think about this is if you say, you've got this curve and we say increasing population density, that puts more fish per habitat unit, and they'll decline in their average survival. If you have fewer fish per habitat unit, you'd expect them to do better. But we can flip this by not changing the fish. Instead, you change the habitat. So if you create more habitat but keep the fish the same, then density goes down. And so that's kind of one way of thinking about habitat as being a sort of mediating factor in changing these density dependent relationships. And so a major role of this model is to try to estimate the shape of these relationships, these density dependent mechanisms, or these relationships. And not only that, but how variable the actual realized values, this is kind of the average relationship, but how variable do the realizations happen around that as well. So, so more along this vein of talking about how we link habitat into this model. So we know that if we look at a river corridor, not all habitat there is equally valuable to the salmon there. Some types are more important. How much more important is the question, and what types are they? So one way to answer those types of questions is to build these fish habitat relationships. So on the y-axis, we've got Chinook par density, and on the x-axis, we have a variety of different habitat metrics. And so this is an analysis that is led by Casey Justice here at CritFic, and the y-axis are from snorkel surveys that have been corrected for imperfect detection. And then the y-axis or the x-axis, I think a lot of these variables came from Champ monitoring program. But the idea is to say, to be able to assign a reach some level of a weighting factor based on the habitat characteristics there. And so we can weight each of these reaches based on its predicted fish density relative to the fish density of the highest reach that has the highest density. And that gives us kind of a relative measure of how valuable is the habitat found within this reach. And use that as a weighting factor, sum up the length of the different reaches by their weights, and then that gives us this total metric of what we're calling weighted usable habitat length. And that sort of represents how much rearing, high quality rearing habitat there is. That's kind of the idea behind this metric. And then we'll try to model some of our life cycle model processes as a function of this weighted usable length. And after you push it through the software, this is the estimation routine. These are the estimates that Casey's derived for. You'll see these abbreviations throughout. This is Catherine Creek, Upper Grand Ronde, Lostine, and Minam. Minam being the wilderness area, of course, probably has the most high quality habitat. Upper Grand Ronde and Catherine Creek have the lowest, and Lostine somewhere in between. So moving actually into the model itself and how we've treated some specific aspects of the life cycle and some results too, I think would be good to show. Lucky for you, we won't be able to talk about the full life cycle. We don't have time to talk about kind of how we treat the ocean, phase as well as the freshwater adult phase. We're really just going to talk about the juvenile aspect of this model. That's really where most of the interesting action is happening anyways. That's where most of the biology or most of the biological data are coming from the freshwater juvenile stage. And of course, for freshwater habitat restoration, that's where those scenarios will play out anyways. So we have paid most attention to how we model the freshwater juvenile dynamics. So just this diagram, it's showing sort of just for one brood year how we separate out and how the different stages feed into the next stage. So I'll step through it piece by piece, of course, not just one thing all at once, but some notation here. Of course, arrows are talking about transitions from one stage to the next, and so on. But so to start off, right, they have to start somewhere, and so we start them at the egg stage. And so we produce eggs in any given year as being the product of spawner abundance at age, by proportion female at age, and fecundity at age. And so here's just fecundity might be an important thing to account for, just because not all fish produce the same number of eggs. These populations are predominantly made up of age 4 fish. Age 5 fish are becoming increasingly rare. So that produces total eggs. Now we've got to turn those eggs into par recruits. And so very common way to handle that problem is to use a Beverton-Holt recruitment function. It's this intrinsically density dependent function. And it has this capacity term. And that's kind of where this asymptote ends up. That's the capacity term. But also implies this sort of baked in under the hood, underneath of this relationship, is this declining egg to par survival versus total eggs relationship. This is what I mean by saying that this relationship is intrinsically density dependent, because the survival that underpins eggs becoming total par is a function of total eggs, and so it declines. And so that's how we've chosen to model that transition. And here now getting into some actual results from the model. So these next couple slides, I'm going to kind of do a similar thing. I'll talk about how we modeled it and then show the results. So on these figures, the relationship itself is kind of what we'd expect. That's what we're talking about, the process model. That's what the biology would predict. And then the variability around that is extra variability not explained by the biology alone. And so the points are just point estimates, and then the shaded region around the lines are 95% credible regions. So that's kind of our first main finding of showing density dependent survival at the par recruitment stage. And so then if you just take your total egg production, multiply it by egg to par survival, and then plot it against egg production again, that backs you out that Beverton-Holt relationship. So that we're estimating it on this scale, but of course underpinning all of it is just the standard Beverton-Holt. So I talked about that capacity parameter quite a bit. So just to relate that again back to where how we get that from habitat. So that capacity term is an estimated parameter in the model, but it's estimated kind of as like a deviate from this relationship, which is also estimated in the model. So we force this through 0, but we estimate the slope of this term that says for every additional weighted usable habitat metric, or every additional kilometer, how much do we expect par capacity to increase? And so that is an estimated term. And then we also, off of that, are estimating these. You can kind of view them as like random effects, I guess, off of that fixed effect curve. Would be kind of one way of viewing it. And then it's these terms that get fed into the Beverton-Holt to build that function. And so this curve gives us this nice mechanism for when we want to talk about restoration. We're going to be doing things like talking about cooling the stream or adding more wood. Well, Casey has those relationships that say when habitat changes, this is how much we expect density to change. and we can plug those the changes in the weighting factors to get a new way of usable habitat length, and just gives us a mechanism for reflecting habitat change in the future, how that might affect recruitment capacity. So that's one kind of the links to habitat in this model currently, is through PAR recruitment. So I talked a lot about other sources of density dependence. And so here, these points are blue. This is just talking about the raw data alone. No model here yet, but just looking at the data, we've got these signals of density dependence. And so this is the longest tagging or longest survival stanza that is monitored from the end of the summer. They're tagged as PAR, and then to the point that they reach lower granite the following early summer, that whole survival term is what's represented here on the y-axis, and then the x-axis is what we consider the total PAR abundance. We had to do some to reconstruct that, but if you know, we do see this pattern of density dependence post recruitment. So, you know, recruitment's the density dependent process, but after the PAR have recruited already, we then see some post recruitment density dependence as well. And so, you know, it's important to account for that, because if we didn't, we would say, okay, maybe in the future we can increase PAR, but we wouldn't be accounting for the fact that those increased PAR might end up surviving more poorly. If we didn't account for this. So it's something important to capture. And then we also want to account for the timing that it's happening, and hopefully some mechanisms. So the mechanism that we're thinking about is size. There's a lot about growth rates being density dependent, and and size being a driver of mortality quite a bit. So yeah, so here is a finding where it does appear that there does seem to be some density dependent growth going on. So this is size at tagging, mean PAR size at tagging, accounting for all individuals, not just those that were large enough to be tagged, but also including fish that were too small to be tagged. So total population mean length against total egg production, standardized by, you know, this is egg density, not just total egg numbers. It's density per weighted usable habitat. And so years where there are more eggs out there, not only do fewer fish recruit, as we previously showed, but they tend to be larger by the end of the summer, or smaller by the end of the summer as well. And that might affect how well they survive later on in freshwater environment. So that's kind of another density dependent growth relationship that the model is estimating. So moving in our next survival stage, so their PAR at the end of the summer, they've been apportioned out. I don't really talk about life history apportionment, but this total PAR gets split out into PAR that will migrate out of the headwaters in the fall, and then those PAR that will stay in the headwaters and overwinter there, and then migrate out in the spring. So there's we separate them out, but then they need to survive that overwintering stage to become small. And so we're modeling that as a size of as a function of size at the end of the summer. So that we're treating this as a size-based survival function for fall migrants as well as for spring migrants. And so, you know, you see some consistency among populations and among life history strategies, but also some heterogeneity too. So some of these populations are either flat, don't show any kind of size effect in their overwinter survival, whereas others do show it, and some even show a declining pattern. So not super consistent among populations or strategies, but there does seem to be some amount of evidence anyways for size-dependent overwinter survival. And then to move them from the PAR size into the smolt size, we have a very simple growth function that translates them. That one is not density dependent, but it does capture this feature where if in years where there were larger PAR at the end of the summer, there are also larger smolt at the beginning of the spring. And so that was a feature that we wanted to account for. This growth function allows us to do that. And then the reason why we need smolt size is so that we can model smolt survival to lower granite as a function of their size. And so that's what's shown in these relationships here. So this is, I'm kind of thinking this is like a delayed effect of density dependent growth. So there's density dependent growth occurring between the time that they hatch and the time that they're measured as summer par at the end of the summer. So that density dependent growth, I think, is setting them up for either better than expected survival or poorer than expected survival for their overwintering phase, as well as their migration to lower granite. And then just to remind everyone that the model is not able to just pull these relationships out of thin air. It has to be consistent with the data. And so if we plot the y-axis of this figure as a time series and overlay the data that it's being fitted to, the data are in blue, the green is the time series. So these points, each point is a different year. Probably should have mentioned that earlier on. And so if we plot those instead of as a scatter plot them as a time series, overlay the data, just shows that the model is, running through the data on both axes. So it's building these relationships, but it also has to do so in a way that it explains the existing data. So yeah, it's not allowed to just go totally wild and explain it come up with any relationships it wants to. It has to be constrained by the data as well. So just to quickly summarize, because I know there are a lot of plots there and a lot of relationships. The way we've structured this, the density dependent flow kind of is, if you have more eggs per unit habitat, you think of that as being fewer resources per egg, which then leads to lower par size and lower egg to par survival. And then lower size affects overwinter survival as well as the size that they will reach by the time of outmigration. And then lower smolt size leads to lower outmigration survival. So that's kind of the cascade of, you could call that the density dependent cascade, I guess. So to kind of try to wrap this up here, just to kind of come up with some conclusions, I think of this model as being a kind of a cohesive way to tie a lot of different seemingly disparate data sources together, kind of blow the dust off of them and make use of them into a cohesive population dynamics model. Quantifies historical dynamics, and it's anchored by empirical data. We did uncover quite a bit of evidence for density and size dependence in freshwater survival. And I do think that the ties that we've made to habitat so far will be useful in restoration prioritization analyses. So the next steps, handful of just finishing touches with the state space model, and then would like to get it published. And then, of course, compiling these future scenarios for that sort of step 2, and then step 3 part of the project, building the simulation model to drive the populations forward and see how they fare. So I think that is all I've got. Happy to answer any questions if folks are interested. Thanks.
Excellent. Thanks, Ben. And we'll go ahead and open up the floor. Feel free, per usual, to type your questions in the chat or unmute yourself, raise your hand. And I'll let you just kind of hold the screen a little bit, Ben, in case anybody needs you to go back in the slides.
Yeah, that's my plan. I also want to make sure I can see the chat just in case.
Yeah, definitely.
Hey,
Amy will
Ben,
be
you
able to
said that a lot of these data, are kind of analyzed independently somewhat, like survival estimates and abundance estimates. How are you integrating those error into your model?
Right. Yeah, really good question, Marika. That was Yeah, so that's the aspect of this being a state space model is so it, when we go to fit to say a smolt trap passage estimate, the model doesn't just take that. We're fitting to it as though it's got uncertainty. And so, one way of treating that smolt trap estimate would be to just take that number and treat it as the number of fish that passed this trap that year in the process model and push it through. But what we're doing is we've got this process model that's predicting a number of fish that we expect to pass the trap that year, and that's kind of like the latent that's coming from all the biological calculations in the model. Then we go and fit that expected value to the observed value, and then we use the standard error of the passage estimate as kind of like our the weighting factor, or it's the yeah, that's the observation error term. Yeah. So we're carrying forward the uncertainty estimates by fitting to those as though they're uncertain data. Yeah.
Excellent question. Thanks, Marika. All right. Anyone else out there? And obviously Ben is available if you guys want to email him or reach out, not put any pressure on you.
Hi, I have a question. I'm not a fisheries scientist, so this is all pretty new to me. But so it was my understanding that the weighted usable habitat length is like an important independent variable in your model. So I'm just wondering if the ratio of WUL to the total river length could be an important metric as well.
I think so. Yeah, I definitely think so. That's something I've wanted to calculate for a while, but I have not done it. I kind of think of that as like almost a metric of habitat degradation almost. I guess not exactly degradation because you need to know the amount of change, but yeah, I definitely do think of that as being an important metric.
All right, and then I don't know if you can see the chat, Ben, and I'll just read it for folks that can't. The folks that can't see the chat. The par numbers are based on snorkel surveys, correct? Have you seen any evidence of snorkelers observing a small proportion of the actual abundance of fish, and actual abundance of fish gets larger? And then there was kind of a correction. Sorry, that's as the actual abundance of the fish gets larger.
Yeah. So really good question, Ron. So the snorkel data were only used in building those habitat relationships. When I'm talking about par numbers that the model's actually accounting for, those abundances are set by really the scale of those is set by the smolt trap out migrants and then the survival terms. So that's what sets the scale within the model. But then for building those habitat relationships, yeah, so those are derived from snorkel counts, and we account for the partial detection part of what you're describing to those data. We have a separate model that has been trained to these paired estimates of marker capture and snorkel surveys, where we can estimate what fraction of the population did they count, and how was that affected by the habitat that's there, so that we can scale up those partial counts that we know that snorkeler didn't count all the fish there, scale those up to an actual estimate of how many fish were there, and then roll that up at the reach level. So those are the kinds of things that Casey's doing. As far as this sort of pattern of where the fraction of the population that you count is a function of the actual population size, that's like getting into these like hyperstability or hyperdepletion type catchability curves, and that we're not accounting for that sort of feature. We say that it's the habitat characteristics that drive the fraction of the population you count, not the number of fish that are there. Yeah, but that's kind of that we could talk about that separately. That's less about the life cycle model and more about how the habitat metric is prepped. Yeah.
Excellent. Great question, Ron. All right. Anyone else out there have questions for Ben?
Oh, hey, Meg. This is Jen. Hi, Ben. This is Jen Bayer. I
Hi,
see
Jen.
on your last slide there that you have a GitHub link. So can you tell us how you're using GitHub and what people might find if they visit that site?
Sure. Yeah, I'd be happy to. Well, with respect to this particular project, the GitHub is private right now. So that's just mostly so that the collaborative team are really the only ones that can get in there and make changes, push pull requests, those sorts of things are sort of just housed within the team itself. Of course, when we go to publish this thing, we will be releasing the code and making it all public. So the way we've set this up for management is to have all the data be in a separate repository, and then all the code for the model and all the post-processing, all that stuff be in a separate repository. Just keeping them separate it helps keep things cleaner, and so that we can see the changes to the data sets be tracked, the versions tracked separately from the version of the model. Those sorts of things help just from a cleanliness, organizational standpoint. But then as far as how we're using the GitHub on the model repo, it's really useful to be able to track where you left off. What was the last thing what was the last change that I made to this model? I can go back and look at the commit history and see. We use the issue tracker quite a bit, where you can post comments and say, hey, this is a problem the model's having. Let me document it. And then there can be a comment thread on there where people post ideas, and you can give updates and you can paste screenshots in and link it to other issues, all those other kinds of things. So using that quite a bit. And then I personally use what's called the feature branch workflow as far for Git workflows. And that has worked out really nicely. The overall idea is that you've got your main version of the model, and then that's always operational. Anytime you don't ever make a change to the main version of the model. If you do want to make a change, say I want to model some aspect a little bit differently or try something out, add a new data set, something like that, I would make a branch off of that main. And we call that a feature branch. I'm going to try out something, make some commits on that branch. If I like it, then I can end up merging it back in. If it doesn't end up working, then I can just chop that branch off entirely and discard it. So that it has been really, really useful for model development. If people go to my GitHub, they won't be able to see this particular model, but of course you can see some of the other projects I've worked on. But yeah, I'm not sure if that was exactly what you're asking for.
That was exactly what I was asking for. Thank you, Ben.
Great.
Thanks, Jen. And then Ron had just added a comment. Thanks for the answer. I would love to chat about this more. I think we are seeing DD relationships with coho on the Oregon coast, but we also have some data that indicates snorkelers observe a small proportion of the actual abundance as the actual abundance gets larger.
Boy,
and I believe
tricky.
that's Ron Constable with ODF&W. Correct me if I'm wrong, Ron.
No, you're right.
Awesome.
Okay. Yeah, we'll have to touch base separately, Ron. That sounds like an interesting problem.
Yeah, I'd love to chat with you about that if you're available.
Great. Yeah, drop me a line anytime.
Will do.
Okay. Any other questions?
All
I'll
right.
ask another one. Wait.
Oh, okay. Go for it, Jen.
I know. I heard. I don't know if I missed something, but I heard you say something, Ben, about the habitat programs, and that it was it eased the processes in general because the programs were similar. Was that? I'm trying to recapture.
Yeah.
So,
So the monitoring, really the biological monitoring programs for each of these populations is very similar. They all have a screw trap. They all have a weir. They all have a hatchery operation system where the smolts are dumped in at the same time. each year. So we can basically model everybody the same way, just plug in different data sets for each population. That's kind of what makes it easier. Yeah.
So that's awesome. And so how about the habitat information, the data used for that? Was that similarly accessible and consistent, or can you tell us about that? We're trying to support access to doing what you're doing, bringing in habitat data along with the biological data about the fish. So is there anything that you can comment make it easier for the next person or for you, or was it surprised me?
No, really good question. In my position, I'm kind of uniquely and very conveniently placed to be the modeler and not the data person. So I am lucky enough to be able to have folks mostly just provide me the data sets, and then I work on the model. And other folks are dealing with much of the messy stuff in the data prep. Although I will say, as far as the habitat data goes, I think a lot of the data that are feeding into those models were collected by some of our staff in-house. Some of our ongoing habitat program here within CritFic. I think we were able to use some of those data that are just generated in-house. So that made it a bit easier instead of having to go outside of the organization to find these data. But yeah, specifics about the data wrangling stuff, I'm not the best one to answer.
Fair enough. There are other people jealous of your data expert support there, but I'll track that down another day. Thank you.
Cool.
And Lori Porter, I saw your hand go up briefly. Sometimes I know I push buttons on accident, but feel free to unmute and ask a question if you are so inclined.
Yeah, I did have my hand up, but maybe I'll ask Ben after the meeting, and Ben, I'll just send you an email where we need assistance in working on something with Pacific lamprey, because our data is not as consistent over time, and with lamprey life cycles, things are very complicated, but we've reached a point in time where we really need some help with developing some models that will work for lamprey. And so maybe I'll talk with you sometime, because it looked like it's possible we could plug in things into this model that we might be able to get to something. But yeah, I'll speak with you later.
Okay.
Thank you.
Cool.
Awesome. Thanks, Lori. Joseph, I saw your hands up. Go ahead.
Hey, Ben, this is Joseph. I can't let you off the hook without a hatchery question.
Sure.
Knowing that these systems have a large hatchery footprint with the programs we have there, how much of these density dependent effects do you think could be attributable to like the parentage, hatchery spawning, hatchery wild spawning, and thinking about kind of some of the results from relative reproductive success studies showing, not everybody is equally successful after they emerge from the gravel, depending on their parents. So can you speak to that, kind of like what your thoughts are and how the hatchery programs affect your model?
Yeah. Well, as far, from the juvenile level, the hatchery smolts are being placed in after many of the density dependent mechanisms that we're modeling are occurring. So we wouldn't be, talking about it at the juveniles competing with natural origin juveniles competing with hatchery origin juveniles, because the only time they're sharing habitat is kind of when on the out migration. So we're not capturing that. If there is density dependence occurring there due to a lot of hatchery smolt being dumped in, that's something that we're not accounting for. But it sounds like you're asking for earlier in the life cycle. So I'm not sure that this model is really able to speak to that specifically. Of course, the hatchery, natural origin spawners, hatchery origin spawners together produce this pool of eggs that we no longer account for who produced those eggs anymore. And then and then all the parts that recruit from those eggs are just treated as hatchery or natural origin. So yeah, I'm not sure if I can really speak too much to your question, especially through the lens of this model.
So
That's fine. We'll
Ben,
we'll continue that debate offline.
Cool.
Joseph, to add to that topic, our geneticists are working on grandparentage analysis. So if a juvenile comes out of the gravel and say they have like hatchery reared grandparents, this new we'll have hopefully the ability to tell that, and so you can potentially in the future get some of those information that, and I'm not sure, Ben, if you'd be able to integrate that in the future into these kinds of modeling, but the technology is getting there.
Yeah, no, we could probably think about ways of modeling relative reproductive success, you know, differentially for hatchery origin spawners and natural origin spawners. I would have to think about specifically how to do it. Probably the easiest way would be like a fecundity multiplier, right? Just assume that, say, if we assume that hatchery origin progeny survive more poorly than natural origin progeny, the easiest way to do that would be to just add an effect to the fecundity and say, well, effectively natural or hatchery origin fish are producing fewer eggs. It's not that they actually produce fewer eggs, but we know that fewer of their eggs will survive. And so that would be kind of the quick and dirty way of doing it. More sophisticated way of doing it would be to somehow come up with adjustments to the Beverton-Holt relationship, I think. And without explicit data to inform it, that would get tricky. So I would think doing it at the fecundity level and coming up based on relative reproductive success studies, try to come up with correction factors to adjust the fecundities. At my first 20 seconds of thinking about this, that's how I would think that would best be accomplished.
All right. Great follow-up, Joseph and Marika. And with that, I think we're kind of starting to wind down. When I send out the follow-up email, I'll provide Ben's contact information so you guys can reach out via email. And I am going to take control again here, Ben.
Cool.
Thank you so much for your presentation. That was absolutely fabulous. I'm going to wrap up with a reminder that some general fish monitoring workgroup information. You can access more information about the project by visiting the project page on pnamp.org. Amy will try to drop the link in the chat in case it didn't happen earlier. I think I skipped over that earlier. The project page contains links to each task page where you can find task descriptions, documents, upcoming meetings, links to previous meetings, and ways to contact the task leads. If you wanted to be added to the distribution list, feel free to shoot me an email. As you heard earlier, our leads are busy on each task and we'll continue to work through the summer. Our next meeting isn't until October due to the fact that everybody gets real busy during field season. I will be sending out a survey with the follow-up email. We'd love your feedback on meeting structure, content, ideas for topics that you would like to see as a tech talk in the future. We want to try to provide a forum for you guys to get information and get some questions answered. The recording of this meeting will be available tomorrow or Monday. This group will convene again, like I said, on October 19th from 10 to 11:30 a.m. And to close out for today, I would like to give a big thank you to Ben Staton for presenting, the fishermen, the FMWG core team, the task leads, and you guys, the participants. We appreciate you being here. So have a great rest of your day and a wonderful weekend. Thanks a lot, everybody.